Okay, good morning, everybody. Boker tov לכולם. Let's get started. So I'll remind you of a couple of things that I was discussing last time. So we're discussing the Minkowski successive minima. So let me remind you what that is. So this is a kind of a first geometric invariant of a lattice. So given a lattice in n dimensions, there's n different numbers associated with it. I see something on the chat just a moment. What's this?
It does not matter.
Okay. So what are these successive minima? So let me draw a picture first. So suppose this is your lattice. I'll draw it like this. I'm drawing a rectangular lattice on purpose. And so this is the origin. And the lattice looks like this. So it's sort of a, the fundamental domain is a rectangle in the plane. This is maybe fundamental domain. And the successive minima are this would be the length of the first shortest vector, and then the second successive minimum would be the length of the next vector, which is shortest but linearly independent of the first. So in other words, lambda I of L is the nth over all possible R of for which the dimension of the real span of R intersect the ball of radius, L intersect the ball of radius R is at least I. So you're looking at all the radii which contain at least I linearly independent vectors, and you're taking the smallest such number to be lambda I, and we saw that there exist vectors v1 up to vn in the lattice such that vi is lambda I again. Okay, and in this definition, the ball here is with respect to the norm that you choose. So you fix a norm in advance, and you have a successive minima with respect to the norm. So typically, if we don't, so for a given norm, we will, if we want to indicate the norm, we will write lambda I with the norm on top, or lambda I with a k on top, where k is the unit ball for this norm. The unit ball with respect to the given norm. If I don't write, if we omit the norm symbol or k, we usually mean the L2 norm. Okay, so those are the successive minima, and then the theorem that we are discussing should be obvious from this picture. It says that the product of the lambda i's is essentially the co-volume. So in this picture that I showed you, the co-volume is the volume of this fundamental parallelepiped. And so in this particular example, this is the product of the sides of this rectangle, which is exactly the successive minima. In general, the fundamental domain doesn't have to be a square or a rectangle. There could be angles here which are not right angles, but they're not going to be very, very far from being right angles in a certain sense. And so the product of the lengths of the sides gives you a fairly good approximation for the co-volume of the lattice. That's the kind of on a first glance, that's the content of the Minkowski second theorem, but it's more delicate than that, as you'll see. So let me write it down.
Can you scroll a little bit up so we can see like the end of the previous page?
Okay, is this better? So, so here's the Minkowski's second theorem. For any L in Rn, a lattice, and any norm, if I look at the product of the successive minima with respect to that norm, oops, sorry, and divide by the covolume, then I'm bounded from above and below by, on the left-hand side, 2 to the n divided by n factorial and the volume of the unit ball. And on the right-hand side, 2 to the n, same quantity without the n factorial. Okay, so looking at this, if you are not interested in constants that depend on dimension and on the norm, this right-hand side is just a constant. It doesn't depend on the lattice. Left-hand side is some other constant that doesn't depend on the lattice. And so what this is saying is that the product of the successive minima divided by the covolume is bounded above and below by constants. So it's essentially close to 1 in some sense, but this close to 1 in some sense depends on the dimension and depends on the convex body. And the so on a first approximation, you're only interested in saying, well, the product of the successive minima are essentially the same as the covolume. On a second approximation, you want to have a better understanding of the exact constants that show up depending on the volume and depending on the norm or on the convex body. So that's the statement, and we're only going to prove this for the Euclidean norm, and we're actually going to prove statement which is stronger and weaker. It's stronger in that the constants are better. It's weaker in that we only work with the Euclidean norm. Oops. So I've replaced the left-hand side by 1, and I've replaced the right. I haven't changed the right-hand side, so you see that this is different from this. So let's just verify that indeed this is a stronger statement than the general statement in the sense that the left-hand side is better. So remark, for the L2 norm, the volume of a ball of radius 1 with the Euclidean norm is kind of a well-studied quantity. There's somebody has their sound on. So this is a well-known quantity, and it behaves like this. Asymptotically, so kind of on a first approximation, not very precise. Okay, this is a bad use of notation. Sort of, I'll just write roughly equal and I'll say what I mean with words. Take n over 2. You take, you take the integer part of n over 2, factorial, roughly speaking. Okay, roughly speaking doesn't really mean up to constants It just means if you maybe, technically it means if you take logs, this is true up to constants, or another way to understand this is, so somebody has,
אופק,
יש מישהו
לא יודע, לא.
אופק, המיקרופון שלך.
טוב.
אופק, המיקרופון שלך דלוק.
זה אופק?
כן.
יש איזו אופציה לכבות את המיקרופון שלנו, אני לא יודע.
ברק, אתה
יכול לעשות לו מיוט.
לא, אני מנסה להבין איך.
בפרטיסיפנט, ליד השם שלו אתה יכול ללחוץ על מיוט.
אוקיי. So, למרות שזה היה מעניין הסנדוויץ' הזה, אבל בסדר. So this is the rough growth of the volume. So this is a well-studied quantity. Sometimes it's denoted by Vn. Let me write that down because we're going. Sometimes this is denoted by Vn. So there's a precise formula for the volume of the unit ball with respect to the Euclidean norm in L2 in general dimension. And this is written in terms of gamma functions. And if you work out what those gamma functions behave like using the Stirling formula, you get this expression, which is relatively precise. And so you see the main term is this n here in the denominator to this power, but there's some correction. Roughly speaking, it's like taking n over 2 and n divided by 2 and taking, so if n is even, you can take the factorial. If n is odd, you take an integer part and take a factorial. So roughly speaking, this is the main term. This, ignoring this constant and ignoring this completely because it's a lower order, and ignoring a little bit of extra with the gamma function, this is the main term in this growth, okay? So if you plug that in on the left-hand side, you see, okay, we have this, and we're plugging it in here. And so the n over 2 factorial moves to the top, and these two cancel. And so we get some quantity which behaves like the product of n times n minus 1, dot, 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 up to n over 2. Which beats 2 to the n by a large margin. So this is going to 0 very rapidly with n. And so if we prove this bound, we'll be proving a stronger statement for the Euclidean norm. Okay, I just wanted to, we're going to see this formula for the volume of the unit ball a few more times. So it's good to get used to it, but I'm just saying for now that this is what we're going to be proving. And it's stronger than this. This we're going to be proving for the Euclidean norm. This is what you get for a general norm. Okay, questions about the statement of the Minkowski's second theorem and what we're going to be proving? All right. So let's
Is the theorem tight in the general case, in the case of a general norm?
Yeah, so I remarked about that last time. It's interesting. It's a good question. So is this tight? So what I showed you last time is that there is one norm for which the right-hand side is tight. I think that's the infinity norm. Yeah, the right-hand side is tight with the infinity norm. That's easy to check. Just with that is Zn. The left-hand side is tight with another norm. It's tight with the L1 norm, and the lattice Zn. Okay, so both of these are tight for some norm. But if you fix your norm, we're going to be discussing this in a moment. If you fix your norm, you might want to know what the tight right-hand bound is and what the tight left-hand bound is. And that's, in general, that's a wide open problem. Even for the L2 norm, it's a wide open problem. So
Cool, thank you.
Important problem. Okay. All right, so let's prove the theorem. So for the left-hand side, we will need, so this is the proof. For the left-hand side, we will need the Hadamard inequality. So let me tell you what that is. If A is a matrix whose columns are vectors, so V1 up to Vn are the columns. Okay? Then the absolute value of the determinant A is less than or equal to the product of the matrix, the products of the lengths of the column, the norm for the L2 norm for the column. Okay, so this is an easy, you can take this as an exercise and we'll be proving it kind of as part of a more general formalism later. So let me write that down. I'll just give you the intuition here and you can think about how you would want to prove it. I'll just write down, we will prove this as part of a general formalism later. It's a good exercise for those who don't know it. Just using the just properties of the determinant and the L2 norm. What's the picture that you should have in mind? So here's a two-dimensional picture. This is V1, this is V2, and the determinant measures the volume of the parallelogram, the absolute value of the determinant. So there's a red rectangle and there's a purple parallelogram. They both have the same volume, and the determinant of A, so it's a picture in dimension 2. The absolute value of the determinant of A is the area of the parallelogram. I don't need this, which is the area of the rectangle, which is the norm of V1 times the height, which is less than or equal to the norm of V1 times the norm of V2. This is the height. Okay. So it's an n-dimensional generalization of this fact that the area of a parallelogram is bounded below by the lengths of by the product of the lengths of the sides of the parallelogram. Okay, once we know that, let's we're assuming the Hadamard inequality. We take vectors in L, linearly independent, whose lengths are these successive minima. So we discussed last week that you can find these vectors, they're in the lattice, they're linearly independent. They don't have to be a basis for the lattice. We don't know that they generate the lattice over Z, but they belong to the lattice and they span Rn. And so let's let L0 be their span over N. So this is some sublattice in general of L. Let's let A be the matrix that you get by making these VIs the columns of A. And so L0 is A times Zn. And so the covolume of L is bounded below by the covolume of L0, right? We had a basically the covolume of L0 is the covolume of L times the index. We proved in the first lecture that if you have one lattice sitting inside another, there's a relationship between their covolumes. And so this number here is an integer, and so we have this inequality, and this is the determinant A, as we saw, because the fundamental domain is spanned by the is the parallelepiped spanned by the columns of A, and this is less than or equal to the product of the VI's, which is the product of the NI's, and this is where we use atomized volume. Okay, and if you move if you move the co-volume over, you get, we've proved this. Okay. Okay, I'm sorry, this line is kind of confusing. This is equal to that. And this is an explanation. Okay. Dividing by the co-volume of L, you get the left-hand side of the inequality that you wanted to do. Okay, the right-hand side is a little bit trickier. So let's take the VI's as before. As I said, the VI's are not necessarily a basis for L. They span a sublattice, L0, as we saw before, but there was a theorem about sublattices in lecture 1, in the first lecture of the course. We had a theorem that says that there exists a basis U1 up to UN in L so that the relationship between the UI's and the VI's is the following. So V1 is M11, U1, V2 is M21, U1 plus M22, U2, and so on. Vn is Mn1, U1 plus Mn, Vn, where all the Mij's are integers, the Mii's are not zero. In fact, we can take, let's write down, we can take the Mii's to be positive, and we also saw that we can take the off-diagonal terms to be less than or equal to be strictly less than the diagonal terms in positive. So, but this is what I need for now. So we have this inequality. Note that it's when you look at this this is part of the confusing thing about all of this business. If you look about this at first, V1 was chosen to be as short as possible, so it can't really be a non-zero multiple of another vector in the lattice. So in fact, these two facts already imply that V1 is equal to U1, right? Again, what's V1? V1 is the shortest non-zero vector in the lattice in L. So it can't be the multiple by an integer bigger than 1 of another vector in the lattice. And so actually V1 has to equal U1. But then you might think, well, V2 was chosen to be the shortest linearly independent V1, so probably V2 is equal to this guy. But that's not really the case. In fact, we saw an example where the VI's don't generate the lattice, and you have to choose other vectors in this triangular fashion. Okay, so that's part of the confusing aspect of this thing. But what we can say is that if you have a vector in your lattice and it's shorter than lambda I, then it's in the z-span of the first I minus 1 of the ui's. So let's prove the claim. So it's not true necessarily that the UIs are equal to the VIs, but they do generate, the UIs do generate all the short vectors over Z. So proof of the claim, by the definition of lambda I, W has to belong to the span over R of V1, Vi minus 1, right? If W did not belong to this span, it would mean that W, V1 up to Vi minus 1 were all linearly independent, and that would contradict the definition of lambda I, okay? So W is in the real span of Vi up to Vi minus 1. Each Vi is in the Z span, in particular in the R span of U1 up to Ui. That's just because of the triangular form of this system of equations. So every one of the VIs is spanned by the UIs with smaller indices. And that this implies that W is in the R span of U1 up to Ui minus 1. But the UIs are basis, so W is in the Z span. So this proves the claim. So now what I'm going to do is I'm going to use yeah, is there a question?
There is I have not really a clearly formulated question, but
Okay.
I'm confused about ties.
Yeah. So
what is,
if you have a tie, let me go back to the definition of the lambda i's. What is this? Yeah. If you have a tie here, if you have a tie, what you're going to see here is you're going to see a jump. So in other words, you're going to see that, say, for example, there's 3 candidates for being lambda 2. 3 linearly independent vectors are all candidates for being lambda 2. Then what you're going to see is that lambda 2 equals lambda 3 equals lambda 4. There's going to be an equality of the lambda i's. And this collection that I'm telling you exists is not uniquely defined. You can rearrange, you can permute the VIs and still satisfy this property. So I'm not really claiming that this is, there's a unique such collection, even up, it's never unique because you can always replace VI by minus VI. That won't affect its length or the span. But it's also not unique in the stronger sense that there could be ties and there could be some permutations here. But I just choose such a collection VI in the proof. And everything I do after that depends on those VIs. Does that answer the question?
partly. Yeah, I think I can work it out in the claim that you're making. Somehow, you need there to be a jump between lambda I minus 1 and lambda I to make this statement, right?
No. I'm just claiming something about a W, which, okay, I mean, if there is a jump,
Yeah.
what you'll get, if there is a jump, it will actually be true that you can improve the claim. That's all that's true. If there is a jump, say lambda 2 equals lambda 4, and W is less than lambda 4, then it's also less than lambda 2. And then this would be improved. That's all. So yeah, in that case, you could have made a stronger statement in that case, but I don't need it. Okay. So now what I'm going to do is apply the Graham-Schmidt procedure to the UIs. And what that does is it creates new vectors, W1 up to Wn, which are orthonormal. So they're orthogonal to each other and they're of norm 1. And they're a basis of Rn, such that for each I, the span of U1 up to Un is, sorry, U1 up to Ui is the span of W1 up to Wi. Right, W1 is the, yeah, okay, this is what Graham-Schmidt buys you. And then you can write the UIs in terms of WIs, so there are coefficients Tij satisfying the following. U1 is T11, W1, U2 is T21, W1 plus T22, W2, and so on. Okay, that just, those coefficients just exist because of this fact. And I'm just using the coefficients that I get from this fact. And let's take any scalars, integer scalars. A1 up to AN. Okay. And I claim that we're going to have the following thing. The Euclidean norm of the linear combination of future coefficients of the UJs is squared. You work in the TIs, the TIJs, and you get this formula. So this line is just plugging these formulas into this, replacing each of the UJs by the appropriate linear combination. But now, since it's the Euclidean norm, I can pull out the WIs are orthonormal, so I can pull them out, and I get a sum over I norm. Sorry, not a norm, just a number. Right? The norm squared of a vector, which is expressed as a linear combination of an orthonormal basis, is this is the Pythagorean theorem, if you want. It's the sum of the squares of the coefficients. So that's what we're seeing here. So this is where I used the fact that we're using the Euclidean norm. So let me just write that down. This is the Pythagorean theorem. This is the L2 norm. Okay, now let's suppose the ANs are not all 0. I'm claiming the following formula. Okay, so these are the same coefficients that appear in the previous formula, and I'm multiplying the ith one by this number, 1 over lambda I squared, and I'm claiming that what I get is bounded below by 1 if the AJs are not all 0. So let's prove the claim. So let's let J0 be the last index for which AI is not 0, i.e. AJ0 is not 0, but AJ0 plus 1 up to AN all 0. Then and I'm going to look at the sum that appears in formula star, and this sum is linearly independent of U1 up to UJ0 minus 1 because AJ0 is non-zero. And this implies that we have this inequality. So let's see. So this sum equals this sum because the only difference is indices bigger than J0, and all of them vanish. All the coefficients vanish. So this sum is clearly equal to this sum, and this number is bigger than lambda J0 because this vector doesn't depend on these vectors. And so again, by the definition of lambda J0, if it were smaller, if this number were smaller, this vector would be too short, contradicting the definition of lambda J0. Now, in both of the formulas that we had before, star and double star, we can replace n by J0 because of the fact that all these coefficients vanish. Let me show you that again. So in this formula, again, in formula star, if you only sum up to J0, you're not changing anything because you're just adding 0 coefficients and you don't have to change the right-hand side. In double star, if you don't, again, for the same reason, if you change I to J0, you won't be changing, you'll be adding, you'll be subtracting some coefficients which are 0. So this is, if we manage to prove this for J0, we'll actually prove this for N. Okay, so the left-hand side of double star is the following expression. It's the sum I less than J0, 1 over lambda I squared. And so I'll write everything down and then I'll go over it slowly. So okay, so first, let me now go back and explain what I've done. So I'm claiming that this is the proof of the claim. So let's first check that this is really the proof of the claim. And so we're proving that this sum is greater than 1. And what's the claim? That's exactly the same claim, except here I have n instead of j0. And I already said that replacing n by j0 doesn't change anything. So this is really what we're trying to prove. So this is the left-hand side of double star. Lambda i's form a monotone increasing sequence. And so if I'm only adding up to the lambda i's up to j0, the largest of the lambda j's is lambda j0, but it's in the denominator, so we have an inequality that goes this way. So the only difference between this term and this term is that this I became a j0. And so this, we get this inequality. I pull the 1 over j0 out. I get this sum, which we already calculated to be in star the norm of, let me remind you what star says. This is star. So I'm plugging star in here. And use the fact that, and then I use this, inequality here. So I've proved the claim, and now let's let a new lattice L prime be the span over Z of a new basis Vi prime, defined as follows. Vi prime is Tj1 W1 divided by lambda 1 Tjj Wj divided by lambda j. So I'm taking the formula that I had here, and I'm multiplying I'm taking this formula here, and I'm rescaling the Wi's by dividing by lambda I. So in some sense, I'm balancing the lattice. The vectors are pointing in the same directions, but the Wi's are pointing after the Gram-Schmidt process. I take this basis given by the Gram-Schmidt process. I have them pointing in the same direction, but I rescale them to make the lattice more balanced. Maybe that's the intuition for what I'm doing. So what star now shows me, or double star now shows me, is that any non-zero vector of L prime has length at least 1. That's what, let's look at double star again. So this is, if you take this formula and you plug it in, you use it for the span of the VIs, you're going to exactly see that it gives us this fact that all these lengths have length at least 1. So that means that the Voronoi cell of L prime contains the ball of radius 1/2. The Voronoi cell of a lattice is the set of points that are closer to 0 than to any other lattice point. All the lattice points have length at least 1, and so all the points that has distance to the origin less than 1/2 are all contained in the Voronoi cell. On the other hand, L prime is obtained from our lattice L by a triangular matrix of determinant 1 over lambda 1 up to 1 over lambda. And this formula here for the lambda i's says that this linear transformation that maps the Wi's to the Vi's is triangular. It's lower triangular. The linear transformation that expresses the Ui's in terms of the wi's is also lower triangular. And if you take the composition of those two maps, there's a map taking the ui's to the wi's. It's lower triangular. Its determinant is 1 over the product of the ti's. The map taking the wi's to the vi's is another lower triangular matrix. Its determinant is the product of the tii's. The tii's divided by lambda I. So the sum total of this is matrix of this determinant. And what that means is that the covolume of L prime is the covolume of L divided by the product of the lambda i's. So moving the lambda i's over, I get that the covolume this is bigger than, this is equal to, let's write it down. This is the volume of a Voronoi cell for L prime. This is greater than or equal to volume of 0, 1/2, as we saw. And so this is lambda 1 up to lambda n divided by 2 to the n. And now moving the lambda i's over and moving the covolume over, we get that, so rearranging, we get this. This is less than or equal to 2 to the n, which is the right-hand side of the inequality. So that's what we wanted to do. Okay, so basically, just to summarize the proof, is some kind of a change of variables where you start with your lattice and you push it in a certain direction. You push it in such a way that it's more or less balanced. All the vectors have more or less the same length with respect to some orthonormal basis, and that's what comes out. So this ends the proof. It's almost 11. I'm going to take a few more minutes and just give some remarks about this second theorem, and then we'll take a break. And so let me mention a couple of questions about this. So, question, what's the optimal form? What are the optimal bounds for this product for a fixed n and a fixed norm? That's kind of an open question that I mentioned earlier, and there's a conjecture, and I want to state the conjecture, and I want to discuss it briefly. So there's a conjecture due to Davenport. From 46, I think. Yeah, 46. So let L be a lattice. And this is some norm, an arbitrary norm. And let delta be the lattice. I'll define this in a moment, but let's just give it a name right now. This is the packing density, the optimal packing density. So I'm going to define it in a second. The optimal lattice packing density for this norm. then the conjecture is that this product, this is just a conjecture about the upper bound, that this product is where this is with respect to the norm. Okay, so this statement is exactly, well, let's move the co-volume so it's easier to compare. This is the exactly the same as the right-hand side of the Minkowski's second theorem, except for the appearance of a new term, this delta. So you're going to see what delta is. Delta is a number that's smaller than 1, so this is a stronger statement than what's known, and this conjecture is wide open. What is delta? Delta is a very important quantity in geometry of numbers that I'm now going to define, this optimal lattice functional density. So delta is defined in 2 steps for a given lattice. So delta with respect to a norm of a fixed lattice L is the suit of the volume of the ball divided by the co-volume of the lattice, such that the balls are destroyed for distinct I'll draw a picture in a moment, and I'll just write down a fact. This is also equal to the this is equal to lambda 1 of L to the n divided by 2 to the n co-volume of L. Oh, hold on a second. Let's see this in 2 steps. Okay. It's the volume of the ball of radius lambda 1 of L divided by 2 divided by the co-volume of L, which is lambda 1 over 2 L again, volume of the ball divided by the co-volume of L. Okay, right now it looks like a bit of a mysterious quantity. I'm going to explain it in a moment. And delta of the norm, so here this formula is all with respect to a fixed lattice, and delta without a lattice, this is the, let's give this guy a name also. What we just defined before, this is the packing density of L with respect to our norm. And delta.
The ball is also
norm,
the norm ball, right? The ball is the unit ball.
Yeah, all the balls here, yeah, thank you. All the balls here are all with respect to the norm. So with respect to the norm. Everywhere. These balls are taken with respect to that norm. And delta is the sup over all L and Rn. Sorry, sup of these numbers over all lattices. And we're going to later see that this is actually a max. This we will see later. Okay, so let's look at this quantity for a moment and understand what we're talking about here. So it's easiest to think about the first definition. So we're taking the ball, and R is a parameter that we haven't determined yet. And we're going to take it, but we want to take a sup. So we want to make R as large as possible because this quantity grows when R grows. So we want to take R as large as possible so that the different balls around the different lattice points are all disjoint. So when you have a collection of balls and they're centered at lattice points and they're all disjoint, this is called the packing of space. And what are we measuring when we have a packing of space? This is the amount covered by one ball, and this is the volume of the fundamental domain. So this is nothing but the proportion of space that's being covered by these packed balls. We're trying to pack as many balls, disjoint balls as you can, and cover as much of the space as you can. So that's why it's called the packing density. Okay? And where did I get the second formula involving the first successive minimum? Well, remember that the Voronoi cell is, you can take the co-volume of L to be the volume of the Voronoi cell. So basically, we're trying to say what's the largest ball, what's the largest size of a disjoint of a collection of disjoint balls relative to the volume of the Voronoi cell. And the largest ball for which this condition is satisfied is exactly the ball of this size, because as soon as the radius becomes bigger than lambda1/2, the distance from 0 to some other lattice point is such that these balls start to overlap. Okay, so this is a mysterious number. I'll say more about that. Let me show you a picture explaining what this number is, and then I'll say something about its history. So this is a picture in 2 dimensions. So here we have a collection of balls. These balls are centered at these lattice points. These are the lattice points here. They're disjoint from each other. If you make them larger by any amount, they're going to start intersecting. So this is the largest possible amount size that these balls can have so that they don't intersect. And what's their radius? Well, if this is 0, and this is maybe the shortest vector in the lattice, so this distance is the radius of the ball is lambda1/2. And what is the number that we care about? The number that we care about is the ratio of the volume of the red domain compared to the volume of the Voronoi cell. It's the proportion of the volume occupied by the red. You see the formula right here. It's the proportion of the volume occupied by each one of these balls relative to the size of the fundamental domain of the lattice. This picture is from the book of Conway and Sloan, which is like the Bible for this kind of, it's called the sphere packing problem. And it's completely open. It's one of the Hilbert questions. And let me just tell you briefly what's known about it. But before I do that, it's a central problem that we're going to be discussing some more. But before I do that, let's just make sure we understand Davenport's conjecture. So this is a number, and this number is always less than or equal to 1, right? Because you're taking the volume of 2 sets, but you're taking the volume of this set divided by the volume of the Voronoi cell, but this is a subset of the Voronoi cell. So this number is always less than or equal to 1. Just write that down. And so in the Davenport question, where did it go? In the Davenport question, we're taking the Minkowski bound, which is just the bound where this term disappears, and we're making it smaller by some number. Okay? So that's why this is a stronger statement. Let me briefly tell you what's known about the this optimal packing density, and then we'll take a break. So I'll just write it down. So understanding delta is a wide open question, and it's included in some sense in Hilbert's list of problems from 1900. So this is he didn't state it in exactly the form in which we understand it today, but it's some special cases are asked about there. Basically, how do you pack balls, Euclidean balls, efficiently in n dimensions? And so it's wide open for any norm. It's also it's wide open in particular for L2 balls. And what's known about it, and that's the kind of the most famous case. And what's known about L2 balls, there's a couple of bounds. And so let's denote by delta n the optimal lattice packing density for the L2 norm in Rn. And so there's a bound 1 over 2 to the n, which we're going to prove. And this is, I'll write down some names and we'll talk about the history later when we get there. So this is something we will do. So this is usually attributed to Minkowski and Lavka, and we're going to give another proof given by Siegel, and we're going to discuss this. So there are lattices for which you can achieve 1 over 2 to the n. There's a very slight improvement with the combination of a lot of work, and so 6, 5, 9, 6, 3, n divided by 2n, 2 to the n, is another lower bound. And this is Venkatesh, 2018. Following work with many people. So if you compare what Venkatesh got, Venkatesh is a Fields medalist. He was one of the recipients of the in the previous round of Fields medalists. And this is not his most famous result, but this is a very nice result. What's the improvement here? So it's very mild. Look at this thing that's known from about 1900 by Siegel, by Minkowski. And look at this term. This is exponentially decreasing. Here we have the same thing exponentially decreasing, and we increase it by a tiny amount, by n, which was done in the 70s, in the 50s by Rogers, to get some constant times n. And then people started trying to improve the constant, and the best constant today is Venkatesh, and this is what he got. Okay, this should be dead then. So this is a very mild improvement. This bound is a very mild improvement over this bound, and it's taken about 100 years, more than 100 years to get this tiny improvement. And then there's an upper bound, delta n is less than roughly 0.67 to the end. And this, I'm sorry, and this only holds when it is large enough. All large n, and here we also have all. So we're interested in what happens for large n. And this is a result of the Planck. And Levinstein in 78. So there's an upper bound, and you see that the upper bound is very, very far from the. This is growing. This is decreasing exponentially, like 2/3 to the n roughly, and this is going down like 1/2 to the n roughly, and that's so there's a huge gap despite more than a century of work, and that's a wide open question with a lot of practical applications. We're going to be discussing that quite a bit in this course, and so we're going to be at least talking about this bound and maybe a little bit about this bound. Okay, so that's the packing density. Questions before we take a break? All right, let's take a 10-minute break and continue.
ברק?
כן.
אז אפשר לשאול כזה שאלה לגבי, אז בתפקיד הבית, בכזה שאלה 4ג', היה צריך...
אני משתדל לו, בכל זאת לשמור על איזה קשר מינימלי. איך קוראים לך?
שבוע.
אתה שבוע, אוקיי, נעים מאוד. כן, מה השאלה?
אז בתרגיל הבית היה צריך לדבר על הלמדה i ברים, שבמקום הלמדה i זה הפעם הראשונה שיש i וקטורים בתעל.
סליחה, פעם ראשונה שיש מה?
בפעם כזה הכדור המינימלי שיש i וקטורים שהם בלתי לומינרית מעל, שהם פרימיטיביים, כאילו.
נכון, כן.
אז כאילו אני בטוח קראתי את השאלה וחשבתי שהיה צריך לראות שאם כזה לוקחים את האלגוריתם החמדני, שכזה כל פעם אתה לוקח את הוקטור הפרימיטיבי הבא, שמשלים את הוקטורים הקודמים, מתי הוא שווה ללמדה i. אז כאילו, נגיד מצאתי שהארבע וקטורים הקצרים הראשונים שאתה לוקח הם תמיד פרימיטיביים.
כן, נכון.
אז כזה, וזה בדיוק הדוק בסרגל הזה שנתת בכיתה. אז כבר רציתי לשאול אם זה כאילו, לא יודע, שאלה ידועה או גרועה.
השאלה היא, ניסחתי אותה קצת באופן רחב. מה שאתה אומר עכשיו זה דבר שהוא ידוע, כביכול ידוע שהדוגמה המינימלית שבה יש דוגמה נגדית, שבה למדה i בר שונה מלמדה i, זה בדיוק הדוגמה שנתתי עם E1, E2, E3, E4, ואז הנקודה שהיא חצי, 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 חצי. אז זה הדוגמה הכי קטנה. ומה שאני רציתי זה לא בהכרח לדבר על האלגוריתם החמדן, ולנסות להבין, אבל זו מין שאלה קצת, בכוונה היא קשה לעשות אותה באופן מלא לחלוטין, אבל מה שמעניין אותי לדעת, ואני לא ראיתי את זה בספרות בשום מקום, מה שמעניין אותי לדעת זה, נניח שאין הוא 10, בוא נאמר את זה ככה, אין פה, זו לא שאלה לגמרי מוגדרת היטב אולי, אבל לדעתי זו שאלה פתוחה, או לפחות זו לא שאלה שראיתי עליה את הספרות, ואני חושב שאין עליה ספרות. נניח שאין הוא 10, האם יש חסריג שבו למדה 1 בר הוא שונה למדה i בר שונה מלמדה i ב7 מקומות, או 5 מקומות, או ב3 מקומות, מה האפשרויות פה? אז אני לא זוכר איך ניסחתי את השאלה, אבל בואו אולי נבדוק רגע. בואו נצליח לעשות נוסח.
זהו, השאלה פה הייתה כאילו, או השאלה הייתה...
אני חושב שטיפה שיניתי את הניסוח, אתה מסתכל על הדף האחרון? אולי לא שיניתי את הניסוח של השאלה הזאת. העליתי דף מעודכן אתמול. לא, שאלתי שאלה לגמרי מדויקת. למה בסי?
לא, אני קראתי את זה לא נכון. זה לא...
אז מה...
יצא שחשבתי על השאלה שגויה הזאת בזמן. אז זה עניין אותי. אמרתי שיצא שחשבתי על השאלה השגויה הזאת הרבה מאוד זמן, אז...
הבנתי.
השאלה שמעניינת אותי בפני עצמה.
השאלה היא מעניינת בפני עצמה והיא פתוחה. כלומר, אני לא יודע אם היא מאוד מאוד קשה, אבל כלומר, יש קצת עניין של, לא יודע כמה היא תעניין אנשים, אותי היא מעניינת זה בוודאי, היא לא קלה. בבי אני, אוקיי, בבי תיארתי את עכשיו אני מבין מה אתה שואל. בבי אני הגדרתי את הלמדה i בר באמצעות האלגוריתם החמדן, ואפשר לשאול, אפשר לנסות להגדיר עוד מספרים, לא לפי האלגוריתם החמדן, אלא לכל i פשוט לבחור את האוסף הפרימיטיבי מדרגה i, שעבורו הוקטור האחרון הוא הכי קצר שאפשר, נכון? זה מה שאתה שואל?
אני חושב שכאילו, אני כאילו רציתי להשוות את הלמדה i בר ללמדה i, ללמדה i אמיתיים.
כן. אז זה...
זהו.
אז זה לא מופיע בשאלה הזאת, אבל זה מופיע רק ככה.
לא, זה לא מופיע, כלומר, כמה שאני מבין, אני פשוט ממש...
מופיע בשאלה 7.
אוקיי.
זה לא מופיע בשאלה 7. אוקיי, יש שאלה דומה בשאלה 7, שהיא לא לגבי הלמדה i בר, היא לגבי עוד מספר שנקרא אלפא i, שהוא קצת יותר, מתנהג קצת יותר...
לא, אני פשוט ממש כאילו, ממש פספסתי כאילו בשאלה ג' ב-4ג' את זה שכתוב שם למדה I בר ולא למדה I.
הבנתי.
אז, אוקיי, אתה אומר זה לא דבר שאתה...
לא, זה גם שאלה מעניינת. אם יש לך משהו להגיד, אז זה מאוד מעניין.
אוקיי.
אני לא יודע שזה פתור. אם אני הייתי יכול להגיד לך שזה פתור, אז לא הייתי... אז אתה אומר שניסית לפתור את שאלה ג', אבל פשוט להוריד את הבר מצד
את
ימין.
הבר, כן. וקיבלתי שכזה 4 ראשונים ל-I שווה 1, 2, 3, 4, אתה חייב כזה, VI חייב להיות שווה, כאילו למדה I בר הוא שווה קצת ללמדה I.
כן.
אבל, ול-I שווה 5 זה באמת לאו דווקא, ואין לי מושג איך להמשיך את זה יותר, כאילו.
הבנתי. באופן כללי, הדרך להמשיך את הדבר הזה לדעתי, אין לי משהו כתוב בראש, אבל הדרך להמשיך את זה, אתה לוקח דוגמה שיש לך, שבה יש לך הרבה טקואים, והטקואים יוצרים לך כביכול את הדוגמה, ובהם יש פער בין למדה I לבין האורך של VI בר, ואז אתה מזיז את הדוגמה טיפה עם העתקה, עם טרנספורמציה לינארית מאוד קרובה לזהות, שמשנה את הלמדה I בטיפה ומשנה את ה-VI בטיפה, ואני חושב שזה יכול לקחת דוגמה שיש בה הרבה טקואים, ולעשות דוגמה נוספת שבה יש את אותה התנהגות, אבל עם פחות טקואים, וזה ייתן יותר אינדקסים שבהם יש את הפער הזה. זה כאילו זאת האינטואיציה שלי בכל אופן.
אוקיי.
אבל אני לא יודע את הפתרון לשאלה הזאת. טוב, אני עושה לי הפסקה כי אני רוצה עוד לחשוב על משהו שנייה לפני שאני מתחיל.
תודה רבה.
Okay, I'm going to continue. So I want to go back a little bit and talk about the Minkowski's first theorem. So we were just talking about Minkowski's second theorem. Let's remind ourselves what the first theorem says and talk about the relationship between these two theorems. So reminder. the first theorem says the following: if L is a lattice, K is centrally symmetric and convex, and the volume of K is bigger than 2 to the n times the covolume of L, then K contains a non-zero lattice point. So this was Minkowski's first theorem. So what's the relationship between first and second theorems? So I claim that the first theorem implies it's essentially equivalent to the inequality lambda 1 to the n is less than or equal to what you see on the right-hand side of the what you see on the right-hand side of yeah. Okay, so this is an inequality, and it has the same form exactly as Minkowski's second theorem, except instead of lambda 1, lambda 2 up to lambda n, it's just the first successive minimum lambda 1 raised to the power n. Okay, so this is obviously weaker than the Minkowski's second theorem. So Minkowski's first theorem is weaker than Minkowski's second theorem. However, notice that we didn't prove Minkowski's second theorem. We only proved Minkowski's first theorem. And so this is an easy statement. Minkowski's second theorem, I wouldn't say it's extremely difficult, but it's trickier. It's by far trickier than proving this statement. So let me show you why this is sort of equivalent to, I'll just show one direction. So why is this equivalent to, let's call this thing star now. And I'll just show you the proof that Minkowski first theorem implies star, and I'll let you think about the converse direction. So given your lattice L, define R0 by the formula. You dilate L by R0 so that after multiplying by 2 to the n, you get exactly the volume of K. So in the assumption of Minkowski's first theorem, you have an inequality here, and R0 is defined so that when you make this dilation, you have equality, precise equality here. So if R is smaller than R0, if you inflate L by R and R is smaller than R0, then you get the inequality that you need in order to apply Minkowski's theorem. So this is chosen. Well, let me first say that this is the same. This formula is equivalent to the formula that says that R0 to the n is the volume of K. K here is the ball. K is the ball radius 1 if we're using a norm. So this means that R0 to the n is the volume of K divided by 2 to the n times the covolume of that. That's a little computation. That's just an easy computation. And so if R is less than R0, you can apply Minkowski's first theorem to obtain that R times L intersect K contains a non-zero vector, which means that lambda 1 with respect to K of R times L is less than 1, right? For any R, because that's just the definition of lambda 1.
Should
Lambda
it not be R larger than R0? I mean,
If I
otherwise you
make
can.
R smaller than R0, then the lattice, I'm applying R to the lattice, not to the convex body. So when the lattice
Yeah.
is small,
Yeah. Sorry.
I could also have done it the other way around. So now taking R to R0, you get that lambda 1 with respect to this K, of R0L is less than or equal to 1. And so now moving things over, so this means that this thing is exactly by rescaling. This is R0 and lambda 1K applied to L. There's something a little bit confusing about the notation. This K stands for a convex body, not for the integers. So in the statement that we're discussing, there's an n here, which is an integer, but the K on top is the convex body responsible for the norm is responsible for. So what we've got is that R0 times lambda 1 to the K is less than or equal to 1. So now raising all of this to the power n and moving R0 over, we get that lambda 1 K of L quantity to the power n is less than 1 over R0 to the n, and R0 to the n we did before. So this is 2 to the n whole volume of n divided by the volume of K, and that's what I think. That's this. That's this. If we use K as the norm ball, then K is just the norm ball, and this inequality is exactly the same as this inequality. And you can also reverse the implication, and you see that the converse is also true. So Minkowski's theorem is a weaker form of the Minkowski's first theorem is weaker than Minkowski's second theorem, but of course the advantage is that it's much easier to prove. Okay, so Minkowski's first theorem, even though it's a simple theorem, it's very, very widely used. So what I want to do now is show some applications of Minkowski's first theorem. I'll show you two applications. So applications of Minkowski's first theorem. The first application will be to diagonal approximation. Both of these applications, by the way, are due to Minkowski already. The first application is due to is in diagonal approximation. What is diagonal approximation? Diagonal approximation is a branch of number theory in which you're trying to approximate real numbers or real vectors or real matrices by integer numbers or rational numbers or rational vectors or rational matrices. And you want to have good approximations where the quality of the approximation is measured using two different pieces of data. The first piece of data is how close is your rational approximation to the real approximation. And the second piece of data is how complicated is your rational approximation, where one way to measure how complicated a rational number is or a rational vector is by measuring the size of the denominator, or the common denominator, it's a vector. So that's a whole field, and kind of the best known early result, which in this field, which many of you have already seen, is the Dirichlet theorem. And so I'm going to state the Dirichlet theorem for those who have not seen it or for those who have seen it, and explain the relation to Minkowski's first theorem. So what is Dirichlet's theorem? I'm going to state it in the form that's needed for approximation of real vectors. So maybe some of you have not seen it in this formulation. So for every real vector in d dimensions, x, and for every q, which is a real parameter bigger than 1, there exists a vector, an integer vector p, and a positive integer q, such that we have the following two inequalities. The norm of x minus 1 over 2 times p, and this is a sup norm, is less than 1 over small q times big q to the power 1 over b, and q is not 0, and it's bounded by capital Q. So this is Dirichlet's theorem. So here p is an integer vector, so 1 over q times p is a rational vector, and q is the common denominator of the entries of this rational vector. And so the first inequality is saying that this is a good approximation. This is a small amount because q is a parameter and it's in the denominator. And this is saying that the approximation has a common denominator which is not too big. Okay? And if you work a little bit with it, you see that this is tight. This is the best you can hope for. The famous special case, which maybe more of you know, is dimension 1, and in dimension 1 you get the following thing. So if I use this inequality and plug it in to replace this q, I get that you can solve this inequality. For every x, you can find, for every real number x, you can find a rational number x, such that the distance between x and q over q is smaller than 1 over q squared. So that's a kind of a classical, easy result in differential approximation. Let's give the proof of this fact in d dimensions using Dirichlet's original proof. And this proof only works for q, which is the dth power of an integer. So first proof. Well, it can't be adapted, but it wasn't adapted by Dirichlet. First proof, and this works for q of a special form, q is t to d, where d is an integer bigger than 1. Okay, so let me just scroll up. So this statement is talking about all capital Q's, and we're now only going to be discussing capital Q's of this special form. And the proof uses the pigeonhole principle, the Dirichlet principle, which Dirichlet spelled out because of this application. And it goes like this. So you subdivide.
You want d to actually be the dimension, or can it be like any integer?
No,
Here,
d is
when you
the
say
dimension.
q-
In this proof, d is the dimension.
Okay.
As I said, the statement is true, and this proof can somehow be also adapted to deal with every q bigger than 1. But for this particular proof that I'm showing, I want d to be the dimension. So I'm going to subdivide the unit q in d dimensions into q, which is t to the d, subcubes of side length 1 over 2. So what I mean is you have AI, you have the cubes look like this. The product I from 1 to b of AI AI plus 1 over t, where AI belongs to 1 over t times, sorry. AI belongs to 0, 1 over 2, etc. Let's draw a picture. D equals 2, t equals 3, for example. So this is the unit square. And I'm going to be dividing it into pieces of this size. Okay? T to the d such pieces. And let's look at the numbers. So let's look at zero integer fractional part of x, fractional part of 2x, etc. Fractional part of 2x, where the fractional part of a vector is the vector formed by the fractional parts of the entries. Fractional part of a number is x minus the nearest integer from below. So basically what I'm doing is I'm taking x and I'm reducing it mod 1. I'm taking 2x and I'm reducing it mod 1, etc. Qx and reducing it mod 1. So these are points inside this cube. And there are t plus 1 of them, right? Because, sorry, there are q plus 1 of them. 0 to q, you have q plus 1 of them, and there are q, which is t to the d, cells in the subdivision. So these are q plus 1 points, and the partition of 0, 1 to the d contains q cells. So there is a collision. So there's some two indices, I less than j, ij between 0 and q, such that ix, jx belong to the same cell in this partition. Ix is Ix fractional part is I times x minus p1. P1 is a vector in ZB. Jx fractional part is jx minus p2. P2 is also in ZB. And the sup norm of jx minus ix is less than 1 over t, because they belong to the same cell, and these cells are just balls of diameter. These cells here are just balls in the sup norm. They have diameter exactly 1 over t. So I get this inequality here, and now if I just try to understand what that means that this is jx minus p2, and this is ix minus p1, which is j minus I times x, and this is minus p2 minus p1. So set where did q go? So let's set q to be j minus I. So q is not 0 because j and I are distinct. And so this is the number between 1 and capital Q, an integer, and P equals P2 minus P1. This is a vector in ZD. And then what I've gotten is that QX minus Q sup norm is less than 1 over 2. And this just means that dividing through by Q, and recalling the Q is 2 to the D, I get this. So that's what I claim. That's the inequality. I got this inequality here. And I also got this inequality. Okay, questions about this? This is kind of a classical proof. Okay, let's do another proof using, yeah.
If you want to generalize it to other norms, the general proof would work the same, but with some kind of constant at the end.
The pigeonhole proof will not work. That's a good question. So if you want to, that's one reason to use the argument I'm about to give, use the argument using Minkowski's theorem that I'm about to give. It's going to work for a general norm, as you'll see in a moment how it works. This proof won't work for a general norm, and the reason is that you want these norm balls to somehow partition the, you want a big ball to be partitioned nicely with no overlaps into small balls, as this picture shows you. And that's true for the sup norm, but it's not true for a general norm. Okay? In general, what you're going to see in general is you're going to see if you replace this norm by another norm, you're going to have this kind of inequality, but this one will be replaced by a constant depending on the norm. And then it's going to become you'll see what the proof that I'm going to show will give you a constant. The proof using Minkowski's theorem will give you a constant depending on it. It's going to be a volume, a certain volume. Okay? Okay. Second proof. So let's look at what we want. We wanted two inequalities. And the first inequality, as we saw before, is if I multiply through by Q, it's equivalent to this. To this inequality. So this, if and only if, only refers to the first line. So this statement and this statement equivalent. And we wanted, so we want.
Malak, I think on the first inequality there, you have x minus 1 over p times q instead of 1 over q.
Ah, thank you, thank you. And we want this with P in ZD and Q in N. Okay? And if you, suppose you have, so this is equivalent, the whole system is equivalent actually to solving this. Okay, 2x minus q is less than q to the, so I've copied the first line, and for the second line, I want to claim that this is equivalent to having q in z, q not 0, absolute value of q less than q. Okay, and the reason these are equivalent is, of course, okay, clearly if you can solve this inequality, you can solve this inequality with the same parameters. And if you can solve this equality and q is not an integer, just multiply everything by -1, And so this will be transformed into a positive number, and both you multiply both q and p by -1. This will not change, and you're happy. Okay, so solving with positive integers is the same as solving with non-zero integers in terms of the role of q. Okay, so and I can reformulate this as saying that this happens if and only if there exists a vector which I want to write as pq in zb plus 1, where q is non-zero. In the body k, which I'm going to define using those inequalities. So y1 up to yd plus 1 and rd plus 1. Satisfying the inequalities, yd plus 1 less than q, yd plus 1 times xi minus pi, sorry, minus yi. Okay, these two things are exactly the same, right? This is a soup norm. So this is a if we want this condition to hold for the vector y1 up to yd plus 1 being equal to this vector p over q, then the first condition means this, exactly this. And if we want this to hold, then that's this. And if we want this to hold, well, that's this. Okay, so these are exactly the same. And the advantage of this formulation is that now L is now this P over Q lives in a lattice. So take L to be as 1, so volume of L is 1, and let's compute the volume of K. The volume of K. Well, what's the shape of K? Well, there are two conditions here. There's the so I'm claiming that the volume. Let me just write it down. The volume of K is 2 to b plus 1, and let's justify that. So repeated integration. The integral volume of K is the integral over, so repeated integration. So we're integrating b plus 1 times, and here we have the indicator function of K. We integrate in this order. So where does the variable yd plus 1 lives? The variable yd plus 1 lives in a I wrote, yeah. The variable yd plus 1 lives in an interval of length 2q. So the internal integral, the conditions on, so the inside integral only depends on this condition, and we get a contribution of 2 times q. And then for each fixed value of yd plus 1, we ask ourselves, where does yi live? And yi lives in an interval of length 2 times q minus 1 over b, centered at this point. So again, there's this, let me change colors. So this describes, so yi satisfying this inequality are in a are in this interval. So this is an interval of length 2 times q to the minus 1 over b, and y b plus 1 in an interval of size 2q. So altogether, we get 2q times 2 times q to the minus 1 over b, d times, which is exactly 2 to the d plus 1. Okay? The q's exactly cancel out. The bigger q is, the bigger this interval is, and the smaller these intervals are, and they exactly wash out. And so by Minkowski, there is such a solution. So Minkowski implies there is PQ in ZB plus 1 non-zero vector in K. And that's not exactly precisely what we wanted. We wanted a vector in ZB plus 1 in K, which is not 0, but also for which Q is 0. For which Q, sorry, the last entry Q is non-zero. So let's talk about the last entry. If this solution has Q equals 0, then what does that mean? That means that the xi's, then the pi's, I'm sorry, satisfy this formula with this being equal to 0, because this is Q. This is 0, so that means that Pi are less than Q to the minus 1 over d, which is less than 1. So Pi is equal to 0. So that this is this. So if there is a non-zero solution to Q, then necessarily Q is non-zero. And so we got the theorem. Let me questions about this. Let me do an extension. Again, I'll go slightly over time, and I'll do an extension to something called the linear forms theorem. So extension. So as Alon said, you can extend this in various directions. One of them is to play with the norm. If you play with the norm, this volume computation will be a little bit trickier, and you'll do a volume computation, and constants will pop out in this part of the proof, and this will affect the statement. You can also extend it by changing the inequalities that you want to solve, the Diophantine inequalities that you want to solve, and that's what I'm going to do next. And so this is called Minkowski's linear forms. Minkowski's linear forms. Yeah. So we take 2-dimension parameters, m and n, for those positive integers. Aij is a matrix of size n by n, a real matrix. And let's denote by Lj's linear functionals on Rm given by using these coefficients. So Lj of x1 up to xm is the sum going from 1 to m, Aij. Aij inside. So I have n linear forms in, so n linear functional, they're linear forms. The statement now is for each Q, you can find a non-zero vector in Zn and another vector in Zn such that for each J. Okay, so we have these n linear forms, and we can find integer solutions, almost solutions, integer near solutions. And so the second statement here says that these integers that you plug into the forms are not very big. And the first statement says that when you evaluate the linear form on this integer input, you get something which is almost an integer output. It's the integer output pj up to this order. So this is a generalization of the previous one. When if you take n to be 1 and n to be d, you get the English here. And the proof is very similar. I'll just give you the idea. Proof, use Minkowski's theorem as above, with L being the integer lattice in n plus n dimensions, and K being the following convex body. The first n coordinates are going to play the role of Q. Let me call these guys Z's. So the Z's are going to play the role of Q's. I think I'm going to set it the other way around. So the sup norm of the Q's is down below by the parameter big Q, and the second requirement is when you evaluate the J linear form on the Q's, you get something which is very close to the YJs. And so if you use Minkowski's theorem with this convex body, you get that. So by Minkowski's theorem, you get that there exists a PQ in Zn plus n non-zero, such that what we want holds. This is star holds. And again, you want to prove that if Q is now, which is now a vector, is the zero vector, because here Q is assumed to be a non-zero vector. Where is this? Q, what you want is this Q to be a non-zero vector. If Q is a zero vector by contradiction, if Q is the zero vector, then from this formula here, this becomes 0, and this is the PJ. And so what this is saying is that PJ is less than Q to the minus n over n, which is less than 1, so PJ equals 0. So just have Q less than. Okay, and that's the proof of the Minkowski's linear forms theorem. Okay, questions about the theorem? Okay, let's take 10 minutes and then I'll show you another application in another topic of Minkowski's theorem, and then we'll move on.
Bob, can I ask a question about Minkowski's second theorem?
Sure.
So you said that for the L infinity and L1 norms, Zn achieves the extremum, the infimum, or the supremum. Is there a characterization for any norm of the lattices which achieve one extremum? Would be rotations of Zn or something?
For this, that's kind of what people do, in all of these problems, is they try to characterize the tight. Let's see, yeah. So in the scoop norm, just a moment. You can ask the same question, exactly the same question for the even for the Minkowski's first theorem. And in general, it's a difficult question.
Okay.
We're going to talk about similar questions. For example, if you want to talk about the soup norm and the achieving the bound of the extremal lattices in the soup norm in the Minkowski's first theorem, not Minkowski's second theorem, then that was an open question for a long time. It's called the Hayes theorem, and it's a resolved the question of Minkowski. So we're going to talk about that one. In general, there's a literature about it, but I don't really know exactly what's known and what's not known about the second theorem. But there's a lot of work exactly in that direction.
Okay, thank you.
All right, let's go on. So now I want to show another example, another application of Minkowski's theorem. So this is another famous application of Minkowski, and this is this type of application was Minkowski's initial motivation for setting up this whole topic. So I told you in the first lecture that this field of geometry of lattices is called geometry of numbers because it's related to a certain branch in number theory, in algebraic number theory. And there are some statements still to this day that have purely algebraic statements that have proofs that depend on a little bit of geometric considerations. So this is going to be an example. So this is Minkowski's discriminant bound. So I'm going to give you a special case of a famous result of Minkowski, which is bounding a certain number called the discriminant, bounding from below a certain number called the discriminant. And I'm giving it in the special case because it's just too much, there's too much overhead to state it in the general case. But the proof for this special case is very, very similar to the proof that you're going to see in the general case. So let me remind you of some things about polynomials with integer coefficients. And so let P be an element of the ring of polynomials with integer coefficients. So this just means that P of x equals a n x to the n plus a n minus 1 x to the n minus 1 plus dot 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 plus a0, ai, and z. And assume P is monic, which means that an is 1. So the leading coefficient is 1. And P is called irreducible over Q if there are no two polynomials, P1 and P2, in with rational coefficients such that the degree of Pi is less than the degree of P. Okay, and those of you who took a course in algebraic number theory, or maybe even sometimes it's taught in the algebra course, they know that if you can actually, oh, I'm sorry, I didn't write down. So there are no such pairs of polynomials that divide P. And those of you who've taken a course probably know a Gauss lemma that says that if you could divide P and P1 and P2 had integer coefficients, sorry, had rational coefficients, and P was monic, then in fact you could take P1 and P2 to have integer coefficients. So that's kind of a famous lemma. So in this definition of irreducible, you'll sometimes see it stated differently, where this these two polynomials are that we assume do not exist are assumed to have integer coefficients, but that's the same. So this is what it means to be irreducible. If P is irreducible, then and alpha is a root of P, then P is the degree of P is the degree of alpha, which just means that any if you have any non-zero polynomial in which alpha is a root of Q, then the degree of p is less than the degree of alpha. So you can't have a smaller degree polynomial of which alpha is a root if p is irreducible. And the idea of proof is that there's a division algorithm with remainder for polynomials. So if p1, p2 are polynomials with rational coefficients, and degree of p2 is bigger than the degree of p1, then there exist, let's call it q and r, polynomials with rational coefficients, such that p2 is q times p1 plus r, and the degree of r is less than the degree of p1. And you play with this. So if you did have, so getting back to this statement here, if you did have such a Q, you'd play with this fact using P1 and P2 instead of Q and P1, and then you get another, and you plug alpha into this entire formula, this will be 0, this will be 0, and therefore this will be 0, and you will have come up with a smaller degree polynomial for which this is true. So this is a well-known fact about algebraic numbers. And another thing we know is if we have this irreducible polynomial and we look at its root, the roots have to be distinct. So also, the roots of p are distinct. And the reason is that if if p of alpha is 0 and x minus alpha squared divided p, so in other words, if alpha were a root with higher multiplicity than 1, then p prime of alpha would also be 0. And this would be another polynomial with integer coefficients and smaller degree for which alpha is a root. So that contradicts the previous fact. Okay. And another thing that I want to tell you in general is, well, first let's define the discriminant of a polynomial like this. So if C1 up to Cn are the roots of P, and they're all distinct, as we said, then we define their product squared, sorry, the product of their differences squared, this quantity is called the discriminant. So this is some kind of famous invariant associated with any integral polynomial, and in fact, you might ask yourself whether this definition depends on the order in which we choose these CIs. But notice that whenever we have in principle, such formulas might depend on the order, but here we're squaring the difference. So whether if you make any change in the orders, you're going to get exactly the same product. So this does not depend on the choice. It does not depend on how we order the roots. And there's a fact about any polynomial, any expression involving the roots of a polynomial that doesn't vary when you permute the roots, and that's called a symmetric polynomial. So or a symmetric formula. So so delta, I'll just write it this way. And I'm going to state a non-trivial, I'm going to require one non-trivial fact from algebra, and that's that if you take any expression which is symmetric in the roots, then the outcome of this expression is always an integer. So fact, if q of x1 up to xn is a polynomial in n variables, it should be n variables, which is symmetric in the roots of p, which means, again, that q of c1 cn is the same as q of c sigma 1 c sigma n for any permutation sigma on these n symbols, then q of c1 to cn is an integer. So whenever you take a polynomial which is monic and you and irreducible, and you plug it into a do I need irreducible? I'm not sure even sure I need irreducible. You plug it into a symmetric formula, the output is going to be an integer, even if the xi's themselves are not integer. And why is that? So idea of the proof idea is fact.
You probably need that you did not say q is an integral polynomial, right? Because otherwise I can just scale it by.
Yeah, of course. This is an integer. Just put it right there. Yeah. Q is an integer, is a polynomial in n variables with integer coefficients. Okay? So an example would be this expression here, right? This expression here, in terms of the xi's, it's a polynomial of total degree, whatever, n choose 2. Sorry, 2 times n choose 2 because it was 2 here. Okay? So it's some polynomial with integer coefficients, and it's got this symmetry property. And then the outcome, when applying this polynomial to the xi's, is always going to be an integer. And what's the reason for this? I'm sort of sketching the proof idea for those who study a little bit of, this is sometimes covered in the first algebra course in second-year algebra, and sometimes it's not so, but it is covered in the course on algebraic number theory, definitely. So let me just tell you very quickly how the proof goes more or less. So the xi's are algebraic integers. Because P is monic. So there's a notion of algebraic numbers, and then there's a ring of algebraic integers, which are the solution of monic polynomials with integer coefficients. And the algebraic integers form a ring, so they're closed. They're closed under sums and products. And so this means that Q applied to C1 up to Cn is also an algebraic integer. Right? We took algebraic integers, C1 and C1 up to Cn, and we plugged it into this, we plugged them into this formula, which is a formula that only uses multiplication and addition. So we stay in the world of algebraic integers. And on the other hand, by the symmetry property, the fact that this expression is symmetric in the roots ensures that this number is invariant under the Galois group. Of the field extension again, I'm not assuming that you really care about this or that you remember all of this, but for those who do, the symmetry basically says that this number is invariant under the Galois group. Again, sorry, there's something confusing here. This is a, just so you notice, this is the value of Xi valued on this polynomial Q, and this is the rational numbers. It's a different font of the Q. And this is the field generated over Q by the Xi's. And so you're invariant under the Galois group, and that means that this number is a rational number. If you're invariant under the entire Galois group, you have to be a rational number, but you're also an algebraic integer. And so any algebraic integer in Q is actually in Z. So that's sort of the proof sketch for this fact.
Can I quickly,
Yeah.
out of curiosity, the extension need not be Galois extended, right? Can you always?
Well, I've added all the roots. No, I've added all the roots.
Ah, you've added all the roots of the
Yeah.
polynomial, right?
We're over R, so there's like, we're over characteristic 0, so there's no
Right.
separability issue, and I've added all the roots. And now what's the statement? The theorem of Minkowski is that suppose all the Ci are real, so P has distinct real coefficients, then the discriminant has a lower bound, and the lower bound is n to the n divided by n factorial quantity squared. And okay, so if you did take a course in algebraic number theory, this is an important statement, and there's a much more general statement which is also true. And in a more general statement, you don't make this assumption about the roots being reals, and you define the discriminant not just as a discriminant of a polynomial, but as a discriminant of a so-called order, which is a subring in the ring of integers. And you can still define this discriminant, and you still get a certain lower bound, and the lower bound will now involve some other data, like how many of these CIs are real and how many are complex non-real, and so on and so forth. But the proofs will always sort of more or less be the same, and this particular proof I can give very quickly, and the proofs use Minkowski's theorem. So let's give the proof. And this is due to Minkowski. So I'm defining linear forms as in the previous theorem about Minkowski linear forms. So these are elements, these are linear functionals on Rn. And let me define them using the coefficients of the polynomial. I take the Xi's and I raise them to the power Cj's, and I raise Cj to the power 0, 1, 2, etc. And those are the coefficients of my linear form. And so, and the Cj's are the roots as we had before. So Cj is here. And we're going to be interested in the values that the yj's take on elements of Zn. On integer valued, on integer inputs. And so let's first talk about the situation where one of the yj's vanishes. So if yj of x is 0 for some x in Zn, let's go back to the definition of yj. So that means that you can plug in the xi's into this formula, and you see that this basically means that Cj is a root of a polynomial. But the degree of the polynomial, we're going up to n here, and we have an I minus 1 here. So as a polynomial, if the xi's are fixed and the variables are the Cj's, this is a polynomial of degree n minus 1. But we already saw that these numbers don't satisfy integer polynomials of degree less than n. And so if yj of x equals 0 for some x in Zn, then we get a polynomial in Z of x for which Cj is a root, xi are the coefficients, and the degree is less than n. So the only possibility is that this is the zero polynomial, which means that x is 0 as a vector. So non-zero integer vectors will not map yj to 0. And so this means that this is true. But now let's look at Q of Ci to be this product. X is fixed, and now we think of this as a function of the Cj's. Well, what happens if we permute the Cj's? If we permute the Cj's by this formula, the dependence of yj on Cj is just that Cj determines it completely. And so if we permute the j's, we're permuting the yj's. And if we permute the yj's, we don't change the value of this product. And so this is a symmetric expression in the Cj's. So it's symmetric. And so this, and we already saw that it's non-zero. And by the fact that I gave you before, it's at least 1. So now we're getting that y1 of x times etc. times yn of x is at least 1 for x in Zn except 0. Okay, now let's define a norm and a lattice. So the norm of a vector y up to yn is 1 over the L1 norm. So it's 1 over n sum absolute value of yj. L1 norm divided by n.
This is here you have some clash of notation. You're on the right hand side. You don't have yj evaluated at something, right? This is a vector.
Right. This is okay. This is a norm at the moment. I'm going to apply this. Maybe it's clear. This is a norm on our end. Okay. Right now, I'm just defining a norm on our end. But later I'll plug in these numbers and the yi's into the norm. Okay? And so is that clear now?
Yes, yes.
Okay, now let's define a lattice. So A will be the matrix 1, C1, C1 to the n minus 1, etc. 1, C2, Cn to the n minus 1. And let's define L to be what you get when you apply Zn when you apply this matrix A to the lattice Zn. So if you look at the definition of the yj's, what you're getting is just y1 of x up to yn of x, the vectors whose coordinates are given by the yi's, where x ranges over Zn. And the determinant of A squared is delta. This is a van der Monde. This is a van der Monde matrix. If you look at the rows, you get the first. Every element is obtained by, every element in a row is obtained by multiplying the previous entry by some number. And there's a famous formula for determinants of such matrices, and it's exactly where did this go? It's exactly the product of the differences of the numbers in each row, and now we're squaring everything, so that's why the determinant of A squared is the discriminant. Let's remember the inequality of means. The inequality of means says that the norm this norm, which is just the arithmetic average of the absolute values, is bounded from below by the geometric average. And use this with y, a vector in L, then we get that the norm of y1 of x up to yn of x is greater than the product of the yi's in absolute value, which is at least 1 by what we had before. Here, y is a of x. And I don't want to pick a 0 there.
It's supposed to be the product raised to 1 over n, right? Here.
In the arithmetic, here it's the product raised to, in the,
No, the second line.
well, the product raised to the 1 over n, yeah, okay, yeah, you're right.
Yes.
But this is also greater than or equal to 1 because you're raising, we already know that, where did this go? We know this. We know this. So if you raise it to the power 1 over n, you also have the same inequality, so we get this. So what that means is that the ball of radius 1 with respect to this particular norm using this particular lattice doesn't contain any non-zero vectors. So the ball of radius 1 intersecting our lattice contains only the 0 vector. And the volume of this ball as the volume, well, yeah, let's compute the volume of this ball. So we're going to use the Minkowski's theorem with this ball playing the role of the compact set, okay? So this is a ball with respect to the L1 norm, but it's been dilated by a factor of n. So I'll write down the formula and then you'll understand why. So the value of the value is 2 to the n times n to the n divided by n factorial. And how do I get this? So let me do that in red. So recall, if I take a pyramid, the pyramid, which is the convex hull of the first n standard basis vectors in the origin, so some tetrahedron like this. So this is kind of a standard calculus exercise, and the big measure gives this guy 1 over n factorial. And what is this ball? This ball is, well, there are 2 to the n of these pyramids because I can restrict this ball. This is the L1 ball, so I can restrict it to the positive sector. I get a pyramid. There are 2 to the n sectors. So that's the source of this. This is the number of sectors. This is the volume of one of these pyramids, and the ball for this norm of radius 1 is the convex hull of plus minus n1 plus minus n2 plus minus n1. Because of this, the n is appearing. This n is appearing because of the 1 over n in the definition of the ball right here. Right. So if this expression has norm 1 and you're a multiple of one of the EIs, then actually you're n times EI for this to have norm exactly 1. And this formula is exactly the formula for which the set of things of norm 1 is given by this shape. Okay? So this shape is the union of 2 to the n of these tetrahedra, and they're scaled here by a factor of n. So you do that n times, you get n to the n, and that's why you get this formula. Okay? So if you, it's an easy exercise. Maybe I didn't explain it well enough, but you can do this test to see that I'm not cheating you. And now use Minkowski. We know that the co-volume multiplied by 2 to the n is bigger than v. If it were smaller than v, we'd have a non-zero lattice point inside, but we just proved that there are no lattice points inside. That's this statement. So I'm using Minkowski with this lattice and with k being the ball radius 1 for this particular norm. And if I work out what that means, the co-volume of L is, so this is 2 to the n times the absolute value of the determinant of A, which is the size square root of the discriminant, is bigger than 2 to the n and factorial, which is the same as the delta is bigger than 2 to the n, which is what I claimed. Okay, so that's the proof of the Minkowski bond. Any questions?
The 2 to the n should cancel.
I'm
here
sorry.
if
2 to
in
the n
this-
Yeah, thank you. There's a 2 to the n here, and there's a 2 to the n here, and it cancels. And it also cancels in the statement. Where is it? It's not there in the statement.
I don't know.
All right, so that's the those are the applications so far that I wanted to show of the Minkowski's first theorem. I want to say something about what we're going to do next. We won't have time to prove the theorem, but we're going to make some definitions. So we saw one geometric quantity that measures the size of a lattice. So we have lambda 1 up to lambda n, which we think of as measuring the geometry of the lattice. And now I want to introduce another parameter, which are called alpha i's. So let's define them. So we will introduce other parameters. Alpha I is defined as follows. I want to remind you of some definitions. So let L0 in L be a subgroup with respect to vector addition. So this means that L0 is the span over Z of some not some elements, R elements in L, and the UIs we can take them to be linearly independent. So why do I say that we saw this? Well, we proved that an additive subgroup which contains R linearly independent vectors is, if it's discrete, it's actually a lattice in R dimensions. And so we can write any subgroup as the span over Z of an R tuple of vectors in our lattice. And L0 is called primitive if there exists VR plus 1 up to V1 in L such that if you can complete this R tuple to a basis of L. And if this happens, we say that we also say that this tuple is primitive. Now, if you have and we saw that this happens if and only if this is something I proved in lecture 1, if and only if the intersection of L with the span over R of L0 is L0. So definitely L0 is contained in this span, but you might have, in principle, it might be bigger, but this is a necessary and sufficient condition for being primitive. This is for lecture 1. And now I want to measure the fundamental domain of such an L0. So R is called the rank. R will be called the rank of L0 notation. I want to define a co-volume of L0. So L0 is not a lattice in R to the R. So L0 is a lattice in the span over R of L0, which is a space isomorphic to R to the R. And in order to define a co-volume, I need to specify a Lebesgue measure on this vector space R to the R. And in principle, since this is a subspace sitting inside Rn, we don't have a Lebesgue measure. We only have a Lebesgue measure up to normalization. We only know what Lebesgue measure means up to normalization, but we can normalize it using the L2 norm, or the L2 inner product restricted to this, restricted to this span. So what do I mean by that? So, so you can define, you can normalize the bed measure on this space by taking the bed measure on R, normalized so that the measure, so let's call this measure N, the measure of the following set, sum over AI WI, AI in 0, 1, is 1 where W1 up to WR is an orthonormal basis. Orthonormal basis of this space. And once we have this normalization, we can define the co-volume of L0 to be N of omega, where omega is a finite number domain, for L0 in itself. So maybe I'll return to this point later in the course, but for now, all I'm saying is if R is a lattice, if L0 is a lattice of a certain rank, then it's a lattice living in, it's a subgroup of a certain rank. I can think about it as a lattice in R to the R, where R is the rank. And that's because the space it lies in is R-dimensional, and it's isomorphic to R to the R. R to the R has Lebesgue measure on it. Lebesgue measure is the unique translation invariant measure on R to the R. And it's assuming that you've normalized it somehow. It becomes unique after you fix a normalization. So we have to fix a normalization. The normalization we're going to fix, there's not an obvious one. There are many ways of identifying this space with R to the R, and they may differ by, the Jacobian may change when you make different identifications. So we have to choose a particular normalization. The normalization I'm choosing will depend on the choice of an orthonormal basis. I already have a Euclidean norm, an Euclidean inner product on Rn. I can restrict it to this subspace, and now I can talk about orthonormal bases in this space. And now I can talk about this object, which is a unit cube with respect to this orthonormal basis, and I can normalize the big measure so that it's normalized to have measure 1. So that's the notion of the co-volume of L0, even if it's not a lattice of full rank. And now I'll just define the alpha i's that we're going to be working with. So define alpha I L to be the infimum of the co-volume of L0, where L0 and L, the rank of L0 is up. And one more comment that we'll get to next time, co-volume of L0, L0 and L, the rank of L0 equals I, L0 primitive. Okay, so these quantities are measuring something about the geometry of the lattice, and somehow they're easier to deal with than the Minkowski successive minima, and they contain similar information. And so next week, I'll tell you a little bit about the relationship between these quantities and the Minkowski successive minima, and I'll tell you why it's better sometimes to work with these quantities than to work with the Minkowski successive minima. Okay, so that's it for today. See you all next week. Unless there are any questions, please ask. But otherwise, see you next week.
The normalization of the Lebesgue measure on the subspace. This is not the same as normalizing with respect to a fixed subset of the ambient space.
Well, what does that actually mean? So if you have a cube in the ambient space, suppose the space is 10-dimensional and this is 5-dimensional, and you have a cube in 10 dimensions, and now you're intersecting it with this 5-dimensional plane, then its 5-dimensional Lebesgue measure is 0. So you can't really use it.
No. What I mean is you take any measure on the subspace and normalize it so that its intersection with the cube in R to the 10.
Yeah, with the cube,
As
it
volume
won't
one.
be the correct normalization with the cube. It will be if you work with a ball, with a Euclidean ball. We're using the Euclidean metric. And then, but then you have to kind of build in a kind of a normalization that involves those numbers Vn.
Okay, that's the same as restricting the inner product to the subspace.
Yes.
Yeah.
Yes.
Okay. Good.
Okay. More questions? Okay. See you everybody next week.
תודה רבה.
תודה.
תודה.
תודה רבה.
תודה.